of what you'll be making. You have the front end side and then you have the smart contract side. For the front end, you'll connect with your Metamask wallet and you'll assign the message. So you can see that right here. You have a simple connect button. You click on the connect button, connect your wallet, and then you'll assign the type data. The data will be all nicely formatted according to EIP712. Hit confirm, and then we have the signature hash outputted on the screen. You can copy that, and then once you have that, you can take that to the smart contract side, which we will divide into its 3 components, RSV and the Foundry test, and then we'll pass that to our smart contract where it will be verified. First things first, we'll start with making the front end. And the front end will be created using Vite and Viem. And the back end, we were going to be using Foundry. Okay, let's start with the front end. So front end, make another folder. So how I have it set up is I have my main folder, and then I'll have this folder, front end, we'll have this folder, and then go ahead and make a new folder, and then we'll call this one smart contract. Okay, so starting with the front end, go ahead and open up your terminal, and let's cd into the front end. There you go. Then we're going to do yarn create Vite to give us a starting template for our front end. Okay, and then we'll just hit dot so that it'll be made right inside the folder for the project name, and then we will select React, TypeScript, and done, and then we'll run yarn to install everything. Okay, and after that's installed, we're gonna run yarn add Viem, which is a library we will be using to connect to our wallet and sign the message. And for this, we'll also be using Metamask. So let's install that. Okay, nice. Let's go. Okay, go and open up front end, and then you'll see there's everything, all this boilerplate, and let's go to app.tsx and src folder. Okay, so we go ahead and delete this, and then I will actually leave the CSS file just for styling of mine, so I don't have to add any myself. And then everything else inside the app component, let's go ahead and delete that. Let's delete that. Okay, now first things first, let's go ahead and import some things that we will be needing. Let's see. Okay, yeah, let's import type address and type hash, and also create wallet client, and custom from VM. And then also import Gorley, which is the test net, from VM/chains. Okay, nice. And then we'll also import VM-window. Okay, actually for the chain it doesn't really matter, any chain will work. Okay, const wallet client equals create wallet client, and then wallet client will take an object of chain Gorley, and then transport, and then transport we will use custom window.ethereum, and for our case that will be Metamask. Nice. Window.ethereum, and then there's a chance it could be undefined, so let's put the exclamation marks so that it will not throw any errors. Okay, next let's go inside the app component, and then let's create a use state for the account, and then set account, and then equal to use state, and then we'll do type address. Okay. Okay, nice. Type address. And then, so if the wallet is not connected yet, we will want to return a button, and then that button will say connect wallet. Okay, and then on click, we were going to want to connect, which we have not made that function. So let's go ahead and make that function. So let's go inside the app component, below the state, or the use state, you want to write const connect. So let's do const connect equals async, and then const and account. Actually, no, sorry, address equals await wallet client dot request addresses, and the request addresses will return the address that was returned by the Metamask wallet in our case. And so we will set account to that address returned. Okay, nice. Set account address, okay, and then on click connect wallet. Okay, let's see. Okay, let's go to our terminal and let's hit yarn dev to start our server. Okay, our server's right here. You can copy this. Let's go to the browser. I'm already at the page, so I'll just hit refresh. Okay, and that shows up, and yes, we can connect. Nice. Okay, let's go back. And then, okay, so if we're not connected, we want to go here. But if we are connected, we want to show something else. So we go if account is defined, then let's return something else. Oops, let's go actually return, get rid of that parentheses, return, okay, return, okay, div, let's have a div, and inside this div we'll have connected. So if you're connected, we want to show them that they're connected, and we will go ahead and display the account address. Nice. Okay, so let's save that. Let's look at the front end, so we connect to our wallet. Actually go ahead and hit next this time. Let's actually get rid of this. Okay, and confirm. Okay, yeah, and it shows the address exactly we wanted. Nice. Okay, so now if we are connected, we want to go ahead and show the button for them to sign the hash, which we still have to make. So, but first let's go ahead and make that button, since we're already here. Button, and then button, and let's say sign for the text, sign typed data. Okay, and then let's do on click, sign typed data. Okay, sign type data, and we're already here. Let's go. So after we sign the type data, we will expect the signature to no longer be undefined. So let's say if the signature is no longer undefined, let's go ahead and display a div with the receipt, and in the receipt let's put the signature. Let's display the signature. I can't see now. signature. There we go. Okay, I spelled that wrong. Signature. Okay, signature, and we never defined that signature. Okay, let's go ahead and create a use state for the signature. Const signature, and then set signature equals use state, and then for this type it will be a type hash. So type hash for the signature. Okay, so yeah, let's go back to this. So we have the button, and then on click we will signed typed data. Let's make this lowercase. So lowercase signed type data, and then signed type data for the text. And then if the signature is no longer undefined, we're gonna go ahead and output the hex of the signature to the front end. Okay, so now we need to create the function for signing the type data. So const sign type data equals async. Nice. Async, and if for some reason the account is not connected, if there's no wallet connected, they shouldn't be able to see this button anyways, but if they can get there somehow, we just want to return. They shouldn't be able to do anything if there's no accounts defined, so I just have return. If account's not defined, return. And then next we'll have this const signature, and this will actually be a locally scoped variable, so let's kind of put underscore to make it clearer. And let's do await wallet client dot sign type data. Okay, sign type data, and you can see this is all the inputs we can pass. So it's a big object of just, I mean, like any form of signed data that you wanted, any form of, or any object that you want to sign. So this takes an object, and the format of this is very important. So, and it's pretty long, so I'll just go ahead and copy this. And all the code is available in the GitHub, and you can just go ahead and copy it from there, or you can type it out while I talk through it. Okay, so I'll go ahead and copy this. Let's go ahead and paste that in there. Okay, so let me walk through this. So we have the signed data type, and this is the structure for EIP712. So we have the account that's going to sign it. This is the account that we're passing with Metamask. Once we've connected to our wallet, we will sign it with this account. Then the domain. The domain is defined in the smart contract that we'll be using to verify it. So the smart contract will be Ethermail, and this is the version, and this is the chain ID. Just these are all here to help increase the security. So like you sign a message for chain ID 31337, it's not able to be used for any other chain. So, and then if the version is different, it's not able to use in like this. If for some reason the contract changed to version 2, version 1 messages wouldn't be able to be replayed or anything. So these are like security measures and all, just the standard of EIP712. So we have the domain. Well, all this together equals the domain. So in the domain we have the name, Ethermail, version, chain ID, and then the verifying contract. And actually for the verifying contract, this might change. So I might have to change later whenever we deploy the contract in our Foundry test. So we might have to come back to this and put a different address, but for now we'll just have this address in there. It should be fine. Okay, and then for the types, so the types, we have two types. We have person and we have mail, and inside of mail there's a from person and a to person, and the contents are of type string. So in JavaScript you can consider these objects, but if you're looking at a Solidity perspective, you have the struct person, and on the struct person then you have the type. Inside the struct person you have the type string, which will be the name, and then you have the address, which will be the wallet. Okay, and then also from the Solidity perspective you have the mail, and inside mail you have the from, which is of type struct person, and then you have to, which is a of type struct person, and then you also have the contents, which is a string. Okay, and so yeah, and then going on, we have the mail, and then inside mail, of course, we already went over. So the primary type is mail. So we're gonna have a mail, and then inside that mail, we're gonna have a person from. So here's our person from. So this is the actual message that we'll be signing. This is more of the the layout or the types of the message that are going to be used inside the message, and then this is the actual message with the data, specific data that we'll be signing. So we have mail, so it's the type. Then we have the message, the from, and then from the from person, the name will be Cal, and then the wallet will be this address. And actually, this address will be the address of the wallet that you are going to sign with Metamask. So if you haven't, this is the standard Foundry address, but if you're following along, go ahead and replace this address with the address from your Metamask. So go to Metamask, go ahead and copy the address you're going to sign this message with. So just copy this and then paste it in here. Actually, I'll just leave it. Yeah, just paste that in there. Okay. And then you have to Bob. Wallet is just a random address of bytes 20. And yeah, and then we have the contents hello Bob, which is just a string, can be anything. Okay, so that's far. So once we have this is our signature. And then once the signature is signed, it will return a 65-byte signature. And then we want to take that signature, and then let's go ahead and update the state. So set signature to signature. Nice. Okay, so that should be done. Yeah, let's see if it worked. So just save everything. Let's go back to the front end. Let's connect wallet. Let's sign the type data. Yeah, so this is the nice thing about EIP712 is that it will show you everything that's going on. So interacting with, this will be the address of the contract that will verify this. So if you go back to the message inside here, you will see right here. So this is this address. So you have the domain, Ethereum mail version 1, chain ID, and then the verifying contract is this, which just shows up right here. Interacting with, and that's that address is the same. And then you have the message, primary type, mail, as we talked about before. And from, you have Cal, wallet. It's actually, yeah, it identified the address with the one we're using. So this is my address. So I went ahead and replaced the address with the name I have written in Metamask. Okay, and then the to is another person struct with the name, Bob, and then a wallet with an address right here. And here are the contents, hello Bob. Okay, and so let's go ahead and just hit confirm. And now we've signed the message. Okay, so this is the signed signature. So let's go ahead and copy this and save it for later whenever we go to verify it on the smart contract side. So yeah, just put it on the bottom here anyway, it's fine, just comment it out. Okay, there's a signature. Yeah, and so that's it for the front end. So the front end's done, and so let's go to the other folder that we made earlier. Let's open up a new terminal and make sure you cd into smart-contract. Yep, okay, and let's do forge init. Okay, yeah, and this is expecting that you have Forge installed and I have some experience with it. Okay, so let's go here, and then you can see that it has a bunch of the boilerplate as always, and we don't need any of this, so let's just delete it all. Actually, keep that there. Let's change it. Sig verify. Let's keep it nice and simple. Sig verify, and let's rename this to Sig verify. Sig verify. Okay, nice. And then let's go to the script and let's delete. Actually, let's just delete the whole file. Let's delete it. We don't need this. Move to trash. And then the test, we will need the test, but test sig verify. Let's rename that. Test sig verify. We don't want the counter. And then let's just delete everything inside here so that we're able to compile. And let's rename this to test sig verify .t.sol. Nice. Okay. Let's see. Okay, let's forge compile. And yes, we successfully compiled. Nice. Okay. And then also, we are going to use OpenZeppelin's EIP712 library to make our lives easier. So let's go and install that. So forge install forge install OpenZeppelin slash OpenZeppelin dash contracts. Oh yeah, okay, and then let's pass dash no dash commit. There we go. Perfect. Let's wait for that to install. Okay. Nice. Okay, that's done. And let's go ahead and import what we will be using from OpenZeppelin. So in OpenZeppelin, we will go ahead and import EIP712 from. Okay, yeah, before we do that, we actually need, let's go to foundry.toml and let's update our remappings. So let's do this. So type remappings equals array string, and let's do at OpenZeppelin slash contracts slash equals lib slash OpenZeppelin dash contracts slash contracts. Nice. Okay, so that's that. Okay. Contracts, make sure I didn't make any mistakes. Oh, and I forgot an S right here. Okay, let's check this. OpenZeppelin contracts. Lib OpenZeppelin contracts. Okay, nice. Sig verify. Let's go back here. Okay, now at import at OpenZeppelin slash contracts slash utils slash EIP first cryptography. So cryptography slash EIP712.sol. Oh, 712.sol. Okay, and then we're actually also gonna need OpenZeppelin's ECDSA library. So let's go import ECDSA from at OpenZeppelin slash contracts slash utils slash cryptography slash ECDSA.sol. Okay, and hopefully I didn't mistype anything. Yes, I did. Okay, utils, cryptography. Okay, looks good. Okay, and then we're gonna do is EIP712. Nice. Okay, and let's go ahead and make the constructor. For our constructor, we don't need to pass anything, but we do need to pass some parameters to the EIP contract. So EIP, and for the first EIP712, for the first parameter, we're going to pass the domain name. In our case, our example, it's going to be ethermail. So ethermail, and that's a string, and then version number, which is 1. Okay, and that's it for the constructor. Okay, and then let's go ahead and define the type hash for the person struct. So this is specific for EIP712 and how you're going to hash it. So you have to have whenever you hash it, you need to hash it with the type hash of the struct that you're hashing. So let's go to make that. So bytes 32, private, constant, mail. Actually, let's do all caps since it's a constant. Mail dash type hash equals kek 256, and then we're gonna write, so mail type hash will be mail, and for mail we have a person that's from, comma, person, space 2, comma, string contents. Okay, nice. And then close parentheses. Let's see. Nice. And then we also need to define the person struct. So let's do person, capital person, yeah. Then the string, space, name, comma, address, wallet. And then let's close the parentheses, but it already, okay, that's fine. And then let's close the quotes. Perfect. And then let's put it in. Nice. So let's see. Let's look at this. So we have mail and the mail struct, and inside the mail struct we have a struct person from, person to, string contents, person, string, and then we define the person struct here, person, string, name, address, wallet. And note that there are no spaces between the parameters, or yeah, the parameters or inputs here. So from we don't have a space, and it has to be exactly like that or it won't work. So make sure that you have no spaces in between each one. Okay, so I'll have it written just like this. And then since we have a struct inside a struct, we're gonna also have to hash it with the type hash of the person. So the person type hash. So bytes 32, private, constant, person. That's all caps. That's the constant person type hash equals kek 256 of person. And then it'll be exactly the same we wrote above, as it was written above. Name, comma, address, wallet, and then let's close the quotes. There we go, semicolon, perfect. So let's look at this, review it. Okay, 256, person, string, name, address, wallet. Looks good. Now, let's go ahead and define the structs. So we have the struct person. And then for our struct person, if you remember on the front end, let's go back to the front end. For 1 second, go src apptsx. So you have the struct person. Inside the struct person, we have a name, string, and then a wallet, which is type address. Okay. Sig verify. Inside a string, name, semicolon, I've got the R, and then address, wallet. Okay, there's a struct person. Now struct mail. If you remember, struct mail is person from, and then person to, and then also contents string. Okay, so we have content string. Nice, and I put that backwards. There we go. String contents. Okay, so we have all that. Now let's go ahead and create the function to verify. So function validate sig, and then this will take mail, struct of type, or input of type mail, to underscore mail, comma, bytes memory sig, and then address signer, so the address that we signed it with, so we can compare, see if the ECR recover was successful. Okay, validate sig, and then throw an error because I never described the visibility. So it'll be public view, and then returns bool, true or false if it failed. Okay. Okay, first things first. We need a bytes 32. Let's hashed from person. So for the struct, you have to individually hash the structs inside the main type. So for this, in this case, we have male, and then inside this we have a struct or a type of person, and then we have another type person. So we have to individually hash those. So whenever you go to hash them later on, we will not hash them all together. These will have to be individually hashed beforehand, and then we hash everything together. And hopefully that makes more sense later on. Okay, if that didn't make any sense right now. So first things first, let's go ahead and create a function that will hash the person struct. So function, let's do encode and hash, because we're gonna go ahead and encode it, code and hash, encode and hash, and I'll take a person. Let's do memory person. Let's put underscore, so it's local input, and then this will be public pure returns bytes 32. Nice. Bytes 32. Okay, let's check. Looks good. And actually, let's go ahead and make this an internal function, and let's put underscore to show that it's an internal function. Nice. So once we get we're expecting the hash, or we're expecting the person struct. So when we get the person struct, we want to ABI encode the person struct in the EIP712 standard. So how that works is we have, so it's kind of bytes memory encoded person equals ABI dot encode just a normal encoding, not encode packed, person, all caps, person type hash. Okay, and we have, okay, so this is actually, you have to be very careful about this. So anything that is not a fixed size, so any dynamically sized variables have to be, their hash has to be passed, not the value. So you need to hash it before you pass it in. So kick activity 6, and since the name is a string, and strings are not, or strings are considered dynamic, so you have to pass the hash, the person dot name, kick activity 6, and also since it's a string, we first have to convert it to bytes 32, person is closing parentheses, nice, and then comma, oh no, there we go, and then comma here. Okay, it's happy now. And then also person dot wallet, which is an address, and it is static type, so we do not need to hash it. Perfect. Explicit, not bytes 32. Oh, not bytes 32, just bytes. There we go. Okay, perfect. And then we get the bytes encoded person, and then we take that encoded person and let's go ahead and hash it. So return kick activity 6 of encoded person. Excellent. Okay, so let's go back to validate sig. So validate sig, we are gonna pass the person into the encode code and hash function, and I will pass mail dot from. Perfect. And let's just copy this whole line. Let's copy this whole line. And then let's do this two person encode and hash mail, and then 2. Nice. Okay, now that we have both people, we can go ahead and put everything together. Bytes encoded mail equals ABI.encode mail underscore type hash comma hashed from person from person at hash to person. Forgot the H, hash to person. And then for the contents, if you remember what I said, strings are not fixed size or considered fixed size. They're dynamic, so we have to pass the kickack to 56 of the contents. But since it's a string, we have to actually convert it to bytes first. So mail dot contents. Nice. Okay. Bytes. Oh, you gotta specify location, memory, encoded, and encode mail. Okay. Okay, now that we have that bytes in, and that bytes memory of the encoded mail, we will pass that to the function provided by OpenZeppelin. So hash type data equals hash typed data b for, and this is the OpenZeppelin function included in the EIP712 library, encoded mail. Nice. Okay, encode mail. So what this does exactly is it encodes it to the standard EIP712, and if you remember about the domain name and also the version and also the address of this contract, it will include that all into the message hash, so that formats everything correctly for you, and you only have to worry about your application specific hashing for, and like in this case it's the mail type hash, the person type hash, and all that, and then the other library will take care of the rest. I mean, you can do it yourself, but it just saves you time and reduces the amount of errors that you can make, amount of chances for the errors that you can make. So okay, so we get the bytes32 hash type data. So now we have recreated the hash data, and then let's go ahead and next we will pass the hash data and the signature to OpenZeppelin ECDSA library, and we will get back the address of the signer, and we will compare the one that we passed as a parameter, and if they're equal, then it was successful. So let's do that. Address recovered signer equals ECDSA dot, did I do that right? ECDSA dot, yes, recover, and then hash type data, comma, and then we'll pass the signature. Nice. Okay, and then let's return recovered signer equal to signer underscore signer, the one that we passed as a parameter. And if they're equal, then we have successfully recovered the signer of the hashed message. Okay, so that's it for the smart contract, and now let's write a test so that we can pass the signature and also so yeah, that we can call this function right here, pass the mail and then the signature and then the signer. Okay, almost done. First things first, we need to import. Let's go and import the contract. Sig verify from src sig verify.sol. Let's create a, oh, did I miss sig verify, sig verify. Sig verify, sig verify, sig verify. Huh, wonder why. Let's see if it compiles. Let's forge. Okay, compile successfully. Okay, successfully. I think it's just saying nothing. Okay. Import. No, not import. Okay. Let's copy this. We need to, let's create a state variable of sig verify contract type. Verify. Okay, and then let's do function. Function setup. This is a setup function for our Foundry testing, and this is specifically named for Foundry, and it always looks for this function to run before it runs any of the tests. So first, before we run any of the tests, we want to actually deploy the contract. So we'll get sig verify. The load. Yeah, sig verify equals new sig verify, and the constructor takes no arguments. Okay, so that's successfully deployed. Let's go function. Let's call this test. Sig verify recovers address correctly. Public. Okay. So, if you remember, we have to pass the mail struct, and we also have to pass the signature from the front end. So let's go ahead and get that signature that we copied from earlier. So depending where you copied it, let's go ahead and get that. So I copied it right here in app tsx at the bottom. So I'll just take that signature and I will paste it for now just right here, a more convenient location. And if you didn't paste it or you lost it somehow, you can just go back to the front end, sign the type data, and just copy it again. Okay, so let's go back here and let's I'll put this on the bottom to get it out of the way for now. Let's decrease this size. Okay. Okay, address signer. We're going to pass the signer that we are expecting to have signed the message. So this will be our wallet address. So address signer will equal, just go ahead and copy the address of the wallet that you signed the message with. So your Metamask wallet, just put it there. And then next we are recreating the data that we signed. Okay, so the data that we signed was of mail. So first we need to verify it was of struct mail. So first we need to create that mail struct. So if you go back to app.tsx, you remember this is what we signed. So we need to recreate it. We need to send all this, or right here exactly, this is what we really need. So we need to send this to our contract. It will take all these parameters, and in the contract we are going to rehash everything, and we are going to compare the recovered address from that hashed data and compare it with the supposed signer. So yeah, let's go ahead and do that. Let's go back to our test. Sig verify dot. We need to type person. So let's go ahead and create the type person. Let's do from person equals sig verify remember the front person was cow, so let's make cow. Okay, and then cow's address was the address of our wallet. So we are the cow, so let's copy our address. Let's do that. Okay, nice. So we have the person, the front person. So let's create the to person. Sig verify dot person. So we can make a variable of type person. So it's to person equals sig cap sig verify dot to dot person, and then the receiver is Bob. Address, and then Bob's address. You can go ahead and copy that from the front end. Copy that, and then let's paste that address in there. Okay, nice. So we have the front person, the to person, and then with that, let's make the mail. Verify dot mail, and then inside that mail, we're gonna have the front person, from person, comma to person, and then we have the message, which was, let's just copy it from the front end so we don't make any mistakes. Hello, Bob. There we go. Hello, Bob. That's that. So we recreated the message, and so we're gonna pass this mail struct to our message, our test. I mean our contract to verify the sign. Okay. Okay. So now we're gonna deal with the signature. So signatures are 65 bytes, and if you know, each digit is half a byte in hex. So right now, if you add them all together, actually you don't want to include the first one because OX is just signifying that it's a hex digit. So okay, R equals this, and OX. Okay, now we're back. Bytes 32 S equals the next 32 bytes, or everything up till the last two digits, which has 64 characters as expected. Okay, so let's put OX to signify it's a hex. And then there you go, and you can see that they're exactly the same size, so 32 bytes each, which is exactly what we want. And then uint8 v equals the last one, which is actually OX1, and uint8. So uint is to signifies that it's 8 bits, so 8 bits in a byte. So that means that v is 1 byte, which is what I said earlier. Okay, perfect. Now let's go. So yeah, after all that hard work, let's just put it all back together. That's bytes memory packed sig equals abi dot encode packed, and then we're gonna pass all these arguments. So r comma s comma b, and the order matters, so make sure you get the correct order. It has to be RSV, because whenever we go to recover the signer, it's going to divide these like we just did, and it has to be in the order, or it will get the incorrect R, S, or V. It'll just, yeah, has to be in this order, RSV. Whenever you pass it to the ECR recover. And yeah, so you might be wondering why I did this, why I didn't just pass this all together and instead of separating it and then packing it again, because I mean we had it already all together before, but for some reason Slitty was throwing a lot of errors for the trying to convert a static 65 bytes into a dynamic type, so this is a way to get around it. Anyways, so we encode packed sig, and then we're almost done actually. Bool success equals sig verify dot validate sig. Okay, and then we're gonna pass everything we just created. So mail, and then sig will be packed sig, and then signer will be this. Ooh, and I misspelled that. So SIGNER, signer. Okay, signer. Now let's see if it compiles. No, it doesn't. Address, missing an S. There we go. See if it compiles. And then sig verify must be storage memory. Oh, okay. So let's need memory. You have to specify the location. Memory. Okay. No visible. Okay, and then we didn't add visibility for the setup function, which make that public. Okay, perfect. Let's forge compile, and that should compile. Excellent. Okay. Okay. Before we before we run this, let's just do a console log so we can see what's going on. Console log. It's just console log success. See if it's a pass or a fail. Okay, so we're ready to run our test. Forge test --mt. Let's take this, copy this, forge mt -1234. Console success. Bool. Oof. Console.log. Oh my goodness. And it was not successful. So what did we mess up? Let's see if I messed up any of these addresses. Let's go back to check here, double check. That's 22266. 22266. Oh, that is different address. Whoopsies. Could go here. Let's go to mail cal. Let's copy this. And let's make it the same here. Let's try it again. Oh, and you can see that if you look at the logs right here, that this was successfully recovered. Nice. So, okay. So if you want to, we can look at the logs for a little bit. So we passed this. Here's we're calling validate sig on our sig verify contract. We're passing it the mail struct. Okay, yeah. Does some calls, hashes the data, encodes it, hashes it. Then it finally passes that data into ECR recover, one of Ethereum's precompiles, with the hash data and the signature. Okay, nice. And then here is the address it recovered, which you can tell is exactly the same as the address that we signed it with, which is excellent. So yeah, F3, yep, see right there, same exact as our wallet. If you go to our Metamask, it's copy it from there, and yeah, it's the same. You just add OX here, OX, yep, exactly the same, same. Perfect. So yeah, we get that recovered, and then it was successful. So yeah, that's how EIP712 works in a nutshell, in a very simple example. Hopefully you learned something, and yeah, if you have any questions, you can join the Discord, leave a comment on the YouTube channel. If you have any ideas for the next video, please join the Discord. And And if you have any problems you experience yourself, feel free to message me and maybe you can make it the material for my next video as well. Thank you for your time and hopefully you learned something.